So we're looking at the second derivative. The second derivative is basically this derivative of the derivative. So this is a notation here. This is the second derivative notation. It's d squared y over dx squared. Now, this is actually squared here. So this dx, if you're interested in why does the notation look like this? It's not a typo. Okay, the dx is actually squared. So this is a change in x times the change in x. So this actually represents a square. Where this 2 here actually doesn't represent a square. It just tells you this is a second change of y. It's actually not squaring y. We're just saying that this 2 indicates the second change of y. So if you're wondering why the notation looks like that, that's why it does look like that. Okay, so the second derivative is basically when we look at the model for our derivatives, the slope of the displacement time is velocity, or the derivative of displacement is velocity. We know that the slope of the velocity time is acceleration, or the change in velocity over the change in time, okay, is acceleration. So that means that the acceleration must be the second change, or second derivative of the displacement time. So this is one way we could kind of frame this and help us put it into context. The second derivative also tells us how graphs change, which means then it must give us some indication of the shape of the graph. And so when we look at the second derivative, we can actually make some inferences about what the shape of the graph is. So we're going to take a look at this a little bit later, but we'll just actually do the second derivative to start. So to do the second derivative, we just first of all take the first derivative. So I take the first derivative of this polynomial using power rule. So it's 9x squared minus 2. Now if I want to take the second derivative, okay, I just do this second derivative. That those 2 primes mean the second derivative. And then I just apply the power rule again. There's nothing special to this. I just do that. So this function then represents the second derivative. So it tells us, for example, if this was a displacement, this function we can plug in time to get our velocity. Here we can plug in the time to get our acceleration. So this is our the cosine graph. We'll calculate the first derivative. So we apply the derivative of the cosine. So it's going to be negative 2 sine 3x. We have to make sure we use a chain rule, so times 3. So then simplifying this, we get negative 6 sine 3x. Then for apply the second derivative, we just differentiate that again. So I just differentiate sine into cosine. And then I need to make sure that I apply the chain rule because of the extra 3. And so I get negative 18 cosine of 3x. Okay, so that represents my second derivative function. So let's practice applying this. So this is the second change of the 5 over x function. So again, I have to find the first change. Okay, so the first change is going to be y prime. So the derivative of this function using the power rule is going to be negative 5 over x squared. And then if I want the second change of that, basically I'm going to differentiate y prime. So the second change is going to be negative 10 over, sorry, it's going to be positive 10 because it's going to be negative 2 times negative 5, so positive 10 over x cubed, and there's my second derivative. So the second derivative is, to do the second derivative, really just applying the derivative again. So we'll do this one here. Y prime is equal to e to the 3x, apply the chain rule, times 3, and then we want the derivative of that function, so the change of the change function. We end up with the second derivative, which is 9e to the 3x. Okay, so this gives us the change of the change function. So let's take a look at some of these graphs and see how these shapes actually relate to each other. So if you take a look at the original function, let's say that that cubic function is my original f of x function. So the blue function here, that's going to be f of x. Okay. From what we know of derivatives, we know that the derivative of the cubic function should be a quadratic function, so that probably is going to be the derivative there. And just to match these parts here, remember that the horizontal tangents here must match the zeros of the derivative function. And notice that the very bottom of this graph, okay, where the slope is the most negative, is going to be through that point there. Okay, so then looking at the derivative of the derivative, so the green was the derivative. Okay, so this function represents our derivative function. Just put that over here. That's our derivative. The red function then represents the derivative of the derivative function. So if we take a look at the slope of the derivative function is 0 here, there is the 0 of the red function. So that matches here. And how does this 0 actually relate to the blue, back to the blue graph? What does it tell us about the blue graph? Well, it tells us that here the derivative is decreasing and it's hit its most negative point, or if you're thinking of velocity, its fastest velocity backwards. So that would be the maximum slope going down. And then it changes. It starts getting less negative. So that point there's actually what we call an inflection point. So notice that the curvature it's getting less and less positive, or more and more negative until here. And then it starts getting less negative velocity through here and more positive. And this gives us some indication of the curvature. So now we can start matching these pieces. Now, really more importantly, we want to match the first derivative to the second derivative, the original function to the first derivative, but there is this property of the second derivative going back to the blue function, which is an original function here. Okay, so that's something that we want to start considering, and that is telling us about where the second derivative is actually going to give us some information about the original f of x function.